Okay. Good morning, everyone. Thank you for joining us this morning. I'd like to begin by acknowledging the traditional owners of the land on which we meet today in Sydney, Australia. I'd also like to pay my respects to both elders past and present. It's with great pleasure that we welcome you today to inaugurate the 7th International Webinar on Construction Materials. This event brings together leading experts and researchers and industry professionals from around the world to share knowledge and discuss innovations and explore future materials. Today, we'll hear from Akmal at Capral Aluminium and Farid from the Institute of Construction Materials. After each presenter, we will have questions. If you can please put them in the chat so that each presenter can address any questions you may have about what they've talked about. And we will start with Akmal.
Good morning. Did you know that worldwide, the aluminium industry accounts for approximately 1.1 billion tons of CO2e annually? Today, we explore how the low carbon aluminium is paving the way towards a more sustainable future, if you could say that. Next slide, please. Good morning and welcome to today's presentation on lower embodied carbon aluminium extrusions. I'm Akmal Nasimi, serving as the Architectural Specifications Manager at Capral Aluminium. With 18 years of experience at Capral, my background includes a bachelor's degree in architecture, complemented by diplomas in computer-aided design and engineering. Next slide, Maeve, please. In recent years, Capral announced its commitment to achieving net zero emissions by 2050. Now, this is a big commitment for us and will require a wholesale changes throughout the business to achieve it. I guess today's presentation about Locale will give you a bit of an introduction to the next few stages that we've got, the steps. I think you've gone one too far, Maeve, on the slides. So it's important for Capral to achieve our target. Got it. Yep, that one. And work towards it. We are the first extruder within Australia nationally to be ASI certified low carbon extrusions. So we'll go through exactly what they are and how that works in the next few slides, and we'll talk about it. So a little bit of information about Capral themselves. Capral have traded in Australia since 1936. We're Australia's largest extruder and distributor of products. The sites that we have all around Australia, there's multiple manufacturing plants, distribution centers, and aluminium centers. So everything is pretty local to the people, and we are trying to reduce all that transport and everything else within that. The main thing that we are proud of in recent year or almost a year now, that we've become ASI certified low carbon distributor. Now the ASI has two portions to it. I'll explain those in detail once we go through the next few slides. Maybe. Thank you. But before we talk about Locale and ASI, let's have a quick chat about aluminium and sustainability. As some of you might already know, aluminium production is very carbon intensive. On the next slide. So aluminium smelters use an electrolytic process to extract aluminium metals from alumina. It takes about 4 to 6 kilograms of bauxite to make 2 kilograms of alumina, which makes 1 kilogram of aluminium. Most of the energy required is at the smelters process. If you jump on the next one. Although energy is required for each step of the process, which adds carbon into the product, the smelting or the conversion from alumina to aluminium at the smelters requires a lot of that. That's because it requires a very high temperature of almost around 2000 degrees to generate the heat that's required for electricity. One back maybe. So in fact, Australian smelters use about 10% of the Australian electricity grid. We only have 4 smelters in Australia, and we are already using 10% of the grid. That means the rest of the cities, the factories, everywhere else around Australia only uses 90% of the electricity grid. So it's a very, very heavy process when it comes to electricity usage. Next one, please. So there are currently 3 options for aluminium extruded here in Australia. Standard extrusions, global average, 12.46 kilograms. Low-cal green, which we're offering as a standard into our building systems market at no extra cost, 8 kilograms. And low-cal super green, which is offered at 4 kilograms. Only until recently, the global average was hovering around 16 kilograms. So that 12.46 is the recent efforts of everyone around the world working towards a greener aluminium product. And that's dropped from 16 to 12 already. So we're heading in the right direction. And Capral obviously is part of that. Why is it important? Maybe. So on this slide, if we have a look at it, we all know aluminium is a critical enabler in carbon-constrained future. It's got properties of strength, ductility, and lightweightness. It supports development. Most of the projects that I work with the architects all require some sort of aluminium. If it's not in the glazing portions, it will be within the building. But if you look at the top 3 products when it comes to the carbon content or CO2e, aluminium tops that list by quite a lot. Steel, PVC, everything else is a lot lower. So it is important for us to ensure we make a move in the right direction and work towards a greener future, I guess. So let's see what can be done about it. Low-cal, introducing low-cal into the market in Australia. We started offering it about, as I mentioned, about 7 months ago. We are the only ASI certified at this product. So the new release product into the market is still slow a little bit for people to understand exactly how that's reduced. There's certain worries that the product will not have the same qualities. As mentioned before, and you will see in the next slide when we go to it on a little short video, the product itself, the strength and everything is still exactly the same. It's the process that reduces that carbon content. I'll let you watch this little short video and then we'll go into a little bit more detail. Let's finish, maybe. Jump on to the next one. So as you can see within the video, there's certain things we can do. It's mainly to do with the smelting process. We can use alternative sources, work together and produce a better product, which is less heavy on the environment. Our intention is to locally extrude the products. That way we're cutting back on the emissions from transport as much as possible. Offer the billets at 8 kilograms and 4 kilograms, minimum 8 kilograms at standard extrusions within the BSG market. And the main thing, I guess, to keep in mind is the ASI certification. How can we claim this product is low carbon? Who is monitoring it and everything else? So we'll go through how that works. If we look at the next slide, when you choose locale, you are making a cleaner, greener choice, obviously, for the future. But as I mentioned before, how do you know that claim that we are providing 8 kilograms and 4 kilograms is true? That's where ASI jumps in, Maeve. If you could just jump onto the... So Aluminium Stewardship Initiative and Chain of Custody is a very important of this brand, a part of this brand. Basically, ASI drives responsible production, sourcing, and stewardship into the global aluminium value chain. ASI certification provides a whole of supply chain platform for the responsible sourcing of aluminium. I'll go through each one of those separately, but within ASI, you're pioneering and independent third-party standards responsible for production, sourcing, and material stewardship. It's easy to state carbon content values for a product, but it needs to be verified by someone independent. And the ASI initiative is all around the world, and organizations can go through this process. So there's two parts to it. ASI certified performance. This performance sets standards, practices for sustainability and human rights principles to be applied by companies. And there's ASI chain of the custody, where every company or every part of the process is linked, and if a factory is not part of that ASI chain, then the final product sort of falls out of the locale brand or low carbon brand that could be offered. ASI performance standards defines the environmental, societal, governance side of things. So if we look at the next slide, the goal is to address sustainability issues relevant to the production. You're looking at everything from business integrity, policy management, emissions, water stewardship, human rights, labor rights. All of that is monitored by the performance standard side of things. So this body comes within and makes sure that at every stage of the production process, you're meeting those requirements. And then there's the ASI chain of custody standards. If you look at the little image on the side there, you've got the first factory, which is ASI, the middle ASI, and the final little shop that's ASI certified. If you remove the ASI certification from that middle portion of the road, basically you're removing the ASI certification from the final point as well. So it's a whole chain that's connected that needs to be kept in mind. If we are purchasing our billets as ASI certified, we as Capral need to ensure we're meeting the ASI requirements, as mentioned in the previous slide, to keep our ASI certification so that when we are providing the material to fabricators into the market, and they are using it on building sites and stuff, they can claim ASI if they are also signed off and ASI certified. If at any point we lose our ASI certification, obviously they will not have that. So it's very important for the link to stay connected. So how does a facility earn the chain of custody certification? It must prove that the end materials that it produces was ASI certified at each stage of the production process. Each facility that meets this requirement is a COC certified entity and can claim it sells ASI certified materials. If there's a break, then the COC status ends and cannot reach the final entity. So the good thing is Capral has become part of that, and we can provide into the market low carbon or low cal green and super green ASI certified products. So always keep the ASI in mind. And as such, you're getting a much better, cleaner product for now in Australia nationally at no extra cost, basically. So that's about it for my presentation. Thank you for listening. And
Thank
if we have
you,
any questions,
Akmal.
no problem.
Does anyone have any questions for Akmal and the work that he does with Capral?
I do, if I can ask.
Yeah, go ahead.
Thank you so much, Akmal. It was really informative to know that we have an environmental material which is widely being used all across construction and I guess other industries as well. But so it was also good to know that there is a body for certifying low carbon products as ASI. But the question was, in terms of technicality, how is the CO2 equivalent amount being technically reduced? Like, is it through using renewable energies? Is it by replacing some materials or processes?
So as mentioned through the slides as well, thank you for the question. That's a great question. The aluminium itself is carbon intensive in when it's being produced, I guess. It's important to note that the smelting process takes a big chunk of that. And it's all because it uses high electricity amounts to sort of get that heat, 2000 degrees up to the required 2000 degrees to be able to produce aluminium. So what this product does, or the way we are working towards a greener product, is we are removing the coal-fired plants powers, and we are trying to use greener sources such as hydro, wind, solar.
Wow.
And these options reduce that electricity usage quite significantly. And as mentioned, within Australia, we only have 4 smelters, right? And these 4 smelters take up 10% of our grid nationally. So you can imagine that you've got all the cities, Sydney, Melbourne, Perth, Adelaide, you've got all the factories, everyone else is using 90% of your grid, where only 4 aluminium smelters are using 10% of your grid. So removing that electricity component reduces quite a bit of that ASI, power requirement for low carbon. And that's where we are making these changes.
Yeah, thank you so much. Good to know.
Yeah.
Thank you. Did anyone else have a question? No? Great. Well, thank you so much, Akmal. We really appreciate your presentation and all of the information you provided us with.
Not a problem. Thank you, Maeve.
Okay, next we will hear from Wafaey from Qorox.
Hi, how's everyone doing?
Good morning.
Well, I don't know if you guys are aware, I'm actually in New Zealand. I'm not in Australia. So we have slightly different requirements when it comes to getting 3D printing off the ground. A little bit quick background about myself. I'm originally from Egypt. I have a degree in architectural engineering. In Egypt, architecture is inside the Faculty of Engineering. And I worked in Dubai, China, New Zealand, and the United States as a project manager, and recently as 3D printing consultant. One of the major challenges that we have with the construction industry overall is that our productivity is very low. And that's one of the reasons why I started to look into automation, because when I moved to New Zealand in 2015, I found that I'm facing the same problems overseas that I'm facing in New Zealand. No matter where you are, you have the same problems: labor and very tight programs, choking points in the supply chain, and we're doing the same stuff all over for the last 30 or 40 years. And I have 3 graphs there. The top one is done by The Economist and was based on research that was done by McKinsey and Co. And you can see the productivity, global productivity of the construction industry around the world is one of the lowest in the economy. So it's way lower than manufacturing and way lower than the average. And the one at the bottom left is actually Australia. And Australia has more recent data. It comes up to all the way to 2021. And the yellow line on the bottom is the construction industry. So it is not doing really well the way we're doing it. And the one on the right is New Zealand. So you can see that this is not one country's problem or one specific region. It's a global issue. So why are we like this? Because the construction industry is a very funny industry. And when there's boom, nobody has time for innovation. And we're in a bust cycle, nobody has money for innovation. So this little cartoon there reflects this. We're all too busy to use a wheel, and we're happy to try to run around with a square wheel instead. And I believe the construction industry is still stuck in the 80s, and this just shows people the difference that happened in the Formula One from the 80s till now. It took under 2 seconds for a pit stop in 2019, comparing to 30 seconds in 2018. No, sorry, so 1980 and 2019. So the world moved quite a bit, but the construction industry is still stuck. This is just a question. So how old do you think 3D printing have been involved in the construction industry? Is it 5 years, 10 years, 20 years? I will tell you that it's actually close to 60. And if you click again. So this was a video of guys in 1936 using a curving machine, putting layers on top of layers, doing on-site mixing, and they were building bunkers because they were worried that the Nazis would invade the United States. This was 1936, and all of the patents expired in 1965, so it's almost 100 years old. But it took a very nice gap, the same thing like electric cars. 3D printed concrete and concrete overall has a bad reputation for being extremely bad, harsh on the environment. But we did the life cycle analysis comparing a house, an actual house, that if we're using 3D printing concrete in it, or we're using timber, or we're using lightweight steel frame. And this was done in the University of Auckland, and it was peer reviewed in the Engineering Journal, Switzerland, and it's published. So we found that over the life cycle of a 3D printed house is actually better than timber. And predominantly timber is a lot better. But you will see in the end of life of timber, this is where timber goes down quite badly, because what's ended up happening is that the timber does not get recycled. Concrete gets crushed and used as drainage metal or used for as aggregate again. But timber, all of it goes into landfill. Also, there's other hidden advantages of low cost of ownership and heating and cooling the house. cooling houses or heating them up. Concrete houses have 18 to 20% more efficiencies because of the thermal mass that they have, and they require a lot less maintenance. That's a reason why we have all of our bridges, all of the main infrastructure are made of concrete, because it's way more durable than any other type of timber, including crossland. So next slide. So right now I'm just talking about generally the types of 3D printers that are available on the market or being used globally. So you have on the left, you have the gantry systems, and on the right there's the mobile system. So the gantry system generally can give you very long straight walls or very long walls, full stop. But I know New Zealand and Australia you'll not be allowed to do this because you need to have thermal breaks, and you will need to have construction joints every 6 to 8 meters depending where you are, and you also need to be covered because it doesn't rain in New Zealand or Australia. It never floods, it never rains, so we're continuously very dry. Now, I'm being sarcastic here, but it's very common in countries that are used to have canopies over the construction sites, especially in Europe and North America, because in winter it's so cold, so they're used to have canopies actually to heat up the construction site. And the mobile ones, which print smaller walls, a lot more quicker to set up on site. If they need it, they can be also under a tent, or they can be under a smaller tent. And both of them can do off-site manufacturing or on-site manufacturing. It really depends on the best application for the product. Overall, it is a lot faster, obviously, to use the mobile systems because you don't have to have all of this canopy before you start. The picture on the bottom left is the guys in the States were, as you can see, it rained, so they had to stop. So as any normal concrete, you will not be able to pour it when it's bucketing down with rain. So 3D printing has multiple applications, and one of them is, for example, doing walls for commercial buildings. So this is a project that we have done here in Hamilton, and it's a daycare. The walls are load bearing and they are 2 hours fire rated. The walls were printed in 5 days, installed in 2, and then they were filled in 1 day. So the whole process of printing these walls and getting them installed was 8 days. They're over 150 square meters. And the biggest advantage we have with that is that you don't need to create formwork. So we were able to print 6 to 7 panels per day. And this is our first really fully 3D printed house. It was done here in Auckland, in a suburb called Paringo. It is 250 square meters, 252 exactly, and it has a combination of retaining walls, external walls, and internal walls. We have also insulation requirements like we have in Australia, but the thing that we have here in New Zealand that you don't have in Australia is we have very high seismic requirements. Because obviously we had earthquakes, we had fatalities, so after Christchurch, they went overboard. We had one of the strangest, if not the strangest, seismic requirements anywhere in the world. And I know that because there's a similar robot like ours in Japan, and they don't have as much reinforcement in the walls as we do. And I've also been to the States and worked with companies in the States where they have hurricanes and earthquakes, and they have the whole variety. And again, they don't put as much reinforcement. But the nicest thing about this house is that it's quite big, and also the design is very unique. Another thing also is infrastructure. So we have printed this stormwater collection system. In New Zealand, we use something called rain gardens, which is effectively this big snake-looking, effectively manhole. It retains the water before it goes to the wetlands, and it gets filled with media and plants, and the plants and media absorb the water. So you have less overflow going straight into the wetlands rather than just flooding it. This is a world first solar passive house to have 3D printed walls. So this was done for a client in Auckland, and it's the same. And Duncan Perth is the architect that worked on it. Initially, it was designed as masonry or cement blocks, and it was replaced with 3D printed walls because you can get the texture. The client wanted something different, and this was really our first house that we had any walls in, and this was in 2022. And again, it was an easy swap. Obviously, you can do a lot of landscaping elements with it. We have done a skate park in Tauranga, and we have done seats for Hamilton and Auckland Council. And the 3D printers give us a little bit of an opportunity that we can use recycled waste material as bulk fill inside the seats. So the seats on the right have waste material embedded in it, and it's the same thing with the small seats on the middle. The small seats in the middle, this was part of a street upgrade project, and they were printed in 2 minutes. Each seat was printed in 2 minutes. Also, there's uses for it as for prefab toilet blocks or prefab amenities for councils. This one was done in Japan. It's not done by us, but it gives you a very good, resilient, and low maintenance asset that the councils can have. There's something that we started to do recently is doing marine habitats, and the picture on the right is from a project that was done in Europe. So they printed a whole coral reef, and it was placed in the Mediterranean, and it's big enough that you can dive through it. And the one on the bottom is Miami. So Miami is flooding because of the rising sea levels. So they need to do new sea walls, but this time they have to make them not just part of precast. The environmental requirements is that they need to create habitats for marine life to reestablish after the disruption that happened during construction. So there's massive opportunity there. I know Australia and New Zealand have a massive issue when it comes to sea levels and flooding overall. So we have all of what you see is not done in New Zealand. The one on the top should be under construction in the Netherlands. It's highway flyover, heavy duty. The one in the middle is in Eindhoven. It's a cycling lane, and the one at the bottom is in China. So all three of them, potentially the top two are using the same system. They're using post-tension cables, and the one at the bottom is effectively cladding. And that's it. There's a very quick video that will explain how the whole thing works. So the company is called Qorox. This is our demo video. The robot generally only needs 2 people to control it, and they don't need to be builders. They're effectively training machine operators, so it helps us with the shortage in workforce. There's a architecture website called ArchiPro. We took the robot there in the viaduct in Auckland, where they have the America's Cup sheds, and we printed these walls. And when we got the robot in 2020, we had Hamilton Council as our first customer, and we printed seats for them in the public demonstration. And it was done in the middle of town, effectively. By having honeycomb shape, we can use 80% less concrete. And right now they're sitting next to the river. And this is our first little wall that we ever did. It's not a big feat, but it just shows another use of the 3D printing. These were the seats that were printed, and right now they're sitting in a place called Emily Place in Auckland. This is the house in Perry Marine, and you can see it during the construction stages. Again, that's the daycare. This is the picture of the wall, and we even do kitchen counter from it. This is the solar passive house was still under construction, and just give you an idea of how it looks like. This is the rain garden, just to show you the scale of it. It's 50 meters long, and obviously we have landscaping elements that you can use for public spaces. And recently we used these ones for rain protection, and this is how we put waste material. These are cladding that was done for Auckland Council, and this is one of the patents that we have done. And these are the houses that we have in the pipeline or the projects. This is an Airbnb and seating for the music school, and this 3-story house, and previously we had a commercial building. So the point that I was trying to make out of all of this is that 3D printing construction is not just for housing. It's not just for infrastructure. It has a massive applications that could be used for across the whole construction industry.
Great, thank you, Wafaey. Does anyone have any questions?
And I have a question, if it's okay.
Sure, go ahead.
Thank you so much. Wafaey, was really informative to know that 3D printed houses are being spread across the world, especially in the neighboring country of Australia. But one question was that, so these 3D printing houses are going to tackle productivity issues in the construction, definitely. And you mentioned that 2 people can build a house now. In terms of, like, the question was, how many stories can a 3D printer make?
Yeah, so there's a couple of things that I want to clarify. First of all, 2 guys can print the walls for the house, not build the whole house. You still have the roof traditionally, and you have to fit up the kitchen and all of this stuff. But what we are actually started to print a house here. It's a show home, and from breaking ground to completing the house, we believe it will be done in 3 months. The average time for a house built in New Zealand is 9 to 12 months. So we effectively cut in the construction by 2/3. How many stories we can do right now, based on the testing that we have done and the requirements, we can do up to 3 stories. So you can have townhouses or medium density housing, or the same thing with commercial buildings. So we can go up to 3 stories.
Thank you so much again. Really good.
I had a quick question, if I may, as well.
Go ahead.
With regards to the printing, the printers use some sort of CNC coding, I'm assuming?
We use a modeling software or slicing software that came with the robot when we ordered it, but it's not really specific for that. We use Rhino 3D, which is a very common parametric design software.
So if you got architects and stuff doing their designs for the projects within a certain software, obviously you can convert.
No, they don't, because all of the major modeling and drafting softwares can export in a format that Rhino uses. So there's either DWG or DXF, or can take files straight from SketchUp or ArchiCAD, sorry. So it's very easy for us to import any architecture file, and then we created our own in-house like small programs that live inside Rhino that generates walls. As soon as we import the model, we get the printing model straight out of it.
Oh,
so it makes the design also a lot more automated.
Excellent. So I guess the one other question that I have is with the finishing of the walls, right? At the moment you've got the layers happening, and you get that pattern or the texture.
Yeah.
You can obviously finish the walls.
I don't know if this zoom again. Can you see?
Yep.
Right.
It blurs it out.
It blurs it out. Doesn't like it. Yeah, if I put it next to my face.
Yeah, that's better. So you get that layering, right? If you want to finish that off, if somebody wants to finish that off nice and
you plaster it.
Plaster. Okay.
Yeah.
Perfect.
So, but we only the house that we have done, the full house was plastered. Everything else is this the only project that we plastered. Every single job.
So it can be done if people wanted to finish it off. That's great. That's a great product.
But when you see it in person, you actually find that it's a lot softer and that has a lot more character and it's even better acoustically because the ripples break the sound waves. So it has a lot better resonance than flat surfaces, and you can paint it in whatever color you want it to, or we can put oxides in it to make it black, green, blue, whatever it is, and you can have fading in and out.
Interesting. Thank you very much for that, Wafaey.
Thanks.
Does anyone else have any final questions? No. All right. Thank you so much. It was a
Thanks.
very
Thanks for
informative
having me.
presentation. Okay. Next up, we have Farid from the Institute of Construction Materials. Farid, you're just on mute. You just need to unmute yourself.
Yeah, can I share my slides on my end? Is that okay?
Yeah, I can stop sharing for sure. Just share your screen when you're ready.
Is it visible? Thank you so much. So my name is Farid from the Institute of Construction Materials, and today we're going to talk about automation in construction. As it was mentioned in the previous presentations, we had some productivity issues, as always in construction, and by nature, this is an industry that is a bit passive in terms of embracing new innovations, and that's why automation is an approach forward for everybody to take in the construction. The content of today's presentation will be, we'll go through a bit of data, safety data, and also just to explain what is the necessity to have automation in construction. A new business approach, as it's being really widely used recently, especially when you go to Bunnings, you can see that even the steel frames or timber frames are being pre-made. So the DIY approach is becoming really popular, and to approach to, like, if any business wants to get an edge in the industry in terms of competition, it would make sense to embrace automation. Offsite manufacturing will be the next topic, and in the heart of an offsite manufacturing, there's going to be an automation. Each automated system will be divided into mechanical design and electrical instrumentation. But we're going to focus more mainly on the electrical instrumentation by zooming into control panel design. And again, inside that control panel, there is a computer element that is called PLC, programmable logic controller. And more specifically, again, we're going to introduce Siemens S7-1200 as a really user-friendly PLC for the business owners who like to embrace automation in their normal daily operation. As for the status quo and why we need automation, basically we need an automated system to eliminate the manual handling in the construction, plus the growing demand for housing as the population grows would determine the need for automation. A bit of a data on the casualties and fatalities in construction. Out of 12 people working in the forefront of construction as a construction worker or laborer, one of them would end up with a major disability issue. And in terms of demographics, these are the comparison between the male and females in the industry. As you may have noticed, 181 compared to 14, and we also have more than 1 million major serious worker compensation claims. There was a statistic actually was saying that in every year there is more than $2.4 billion of insurance claims because of construction related injuries. And just imagine that what happens if we can save that money, save lives, and also invest that in some other areas. Housing statistics and population growth is another push for us to move faster towards automation. These are the graphs we see. On the red line, it's the population change in Australia, published by Australian Bureau of Statistics. And the project completions as well on the blue line, you can see. In 2020, we had a major drop in the population change, probably because of COVID, but then suddenly it ramped up again. And bad news for us, project completion right now in 2024 is way lower than the population growth. That's probably one of the main reasons that the housing prices are to the roof. New construction business approach for a DIY, do-it-yourself. Mainly, most of the families are getting interested in that because of construction costs are again high. So everyone's thinking about building it themselves. So if a construction business in Australia wants to take a lead, they must find a way to build these prefabricated elements somehow. And that's how they can do it. Later on in the future slideshows, I'll show you how to design a control panel. Really, in a basic level, you're probably going to need a proper degree for that, but it's going to be an opening in case people are wondering how to start an automation project. Less labor intensivity would be the benefit. A DIY project is becoming popular, but there is a downturn here as well, as it minimizes the architectural flexibility. So everything would be designed in a cubic way, as opposed to a 3D printed house, which enables curvatures in an architectural design. Offsite manufacturing will have controlled safety measures. It's faster, it's easier to install, and it also addresses the skill shortages, the labor availability in the market, caused by many issues. So, but one of the questions I have for our audience, if somebody can help me address this question at the end of the slideshow, is that how we can address the architectural flexibility caused by the modular designs in the offsite manufacturing. So if you imagine the concrete panels being made, all of them are in a flat surface, fair to say more than 95% of them. So how can we create an automated system that would give the architecture a pleasure for the design? Any automation system would have 3 steps: the project initiation, design, assembly, and operation and maintenance. So if you're planning to open up an offsite manufacturing plant, you must consider these 3 steps. Operation and maintenance will be probably it will take most of your budget investment if you're looking at the long-term execution. That automated system would have, let's compare that with a human body. Any automated system would have a skeleton and a muscle, plus a system that would make the decision. So that part that would hold the structural integrity of the automated system. So most of the time they are steel, they don't have any movement. We also have hydraulics, pneumatics, and motors as the moving parts which would mimic the muscles of a human body. The skeletons will be the frames. And for the neural network, the decision-making part of that automated system, we would have these control panels. The industrial control panels are computers and wires, plus the sensors that will make a decision for us. So I say, giving you an example about conveyor belt, you want a conveyor belt to stop rolling once an object is detected at one end, and again start rolling once the object is removed from one end. So that decision would be made by something called a control panel, and these control panels have a PLC at the heart of them. These are the main elements of any control panel. We have the box, or Americans would call it enclosure. The PLC, that's, I guess, the brain of any automated system. Based on the input and outputs, this PLC module would decide a movement. We have the DIN rail slim relays that converts. Okay, so let's move one step back to the PLC. This module is run on a 12-volt DC input and output, but most of the huge elements on site in the factory, they are really energy intensive. So this transition between 12-volt DC to, let's say, 120-volt AC is being done by this DIN rail slim relay. One end of this relay is connected to the PLC, the other end is connected to the actuators on site, plus a few terminal blocks as well. We also have wires. In terms of wiring, the size of the wires will be determined by the amount of current and voltage going inside the wires. A PLC can be programmed in 3 different ways. The most user-friendly one is ladder logic. It's basically a drag and drop system, and also it's not a new approach. It's been there for more than 30 or 40 years. Well, actually, Siemens S7-1200 is a patent that was licensed 30 years ago. And the ladder logic is also the same approach as well. We have a structured text for more complex programming challenges, and function blocks, which are again addressing the complexity in your system. But in most of the cases, ladder logic would answer your need. For Siemens S7-1200, which was chosen for typical construction automation, you will get inputs and outputs. On the top rail, you have inputs, and at the bottom rail, we will have the outputs. So once a sensor sends a signal into the input part of the PLC, based on the program, based on the ladder logic program that you've downloaded to the PLC, there's a certain output signal going out to the field instruments. Let's say if a sensor detects an object, you want a motor to start turning on and start rolling. On this ladder logic example on the right side, so the left one is just a schematic of the PLC Siemens S7-1200. On the right-hand side, we have an example of ladder logic. So let's say on rung 1, possibility number 1, if input 1 and input 2, these are in series, so both of them must be true in order for the first output to be triggered. If input 1 and input 2 are open, output 1 would be triggered. On the rung 2, possibility number 2 that we are programming in computer, if input 1 and input 3 are in this format, then output number 1, 2, 3 will be triggered. We have parallel formation as well, so that will be an OR, input 4 or input 5, then output number 2. So these inputs are going into the top rail of the Siemens S7-1200, and the output signals will go out from the bottom rail. There's a whole proper online course if you're interested. You can get enrolled in that for free on our website. The conclusion will be we need automation, because let's not be so much passive about innovation in construction. There are casualties, there are housing demand going up. So automation is a necessity these days, especially for construction businesses who like to thrive in this competitive market. And also industrial control panels are the way to go. Thank you so much. That was my presentation. Yes, you're mute, mate.
I was just asking if anyone had any questions. Sorry. No?
I have a question.
Oh, cool.
How do you see this being applied on small residential buildings or developments?
Sorry, what was that again? Wafaey.
How do you see the PLC design being used for residential houses and smaller commercial developments?
Smaller commercial development. So the PLCs are normally, or any control panels are for factories. So if you're going to transit the on-site manufacturing, so say instead of taking materials to the site, we're going to shift that into a factory, being pre-made and then transport to the site, assembly only. The PLCs can be used on that, but there must be some sort of applications for on-site assembly and building as well for commercial builders. For simple, I guess I've seen bricklayers are using small conveyor belts. Pretty sure that you've seen bricklayers using small conveyor belts, but it's constantly running. If they have a simple control panel, control box next to the belt, then with a bit of a sensor at the end, then they can control the movement of the belt on site as well. That's just an example.
Okay. So what I'm trying to figure out is how can it be also applicable for example, for 3D printing and for other automation that we need on site. Because, for example, one of the challenges that we have overall is having the material supply and having a continuous supply for the pumps and restocking the silos, because you will not have an infinite silo. You'll end up being restocked, and the controls for all of this needs to be somehow integrated with the amount of materials being pumped out. So you increase the efficiency of material delivery and you reduce the waste from there.
Yes, definitely that can be used for pumping concrete. It's a different from the robotic arm, I guess. I'm not so familiar with the 3D printed elements, 3D printing elements. My understanding is that there's an arm and there's a pump. So for that pump, you're saying having a control panel would help the efficiency.
Yeah. And the arm itself is clever enough. The pumping part is the dumb part. It doesn't have any brains in it, so it needs to be fed. And right now, the feeding is everything is happening manually. So we have to fill up the silo, and the silo pushes the material into the pump, and then the pump pushes the material through a hose and the robotic arms. So the robotic arms are fine. It's just the material end that requires a lot of development still.
That's a proper project, Wafaey. Optimize the pump. But
anyway, okay, that was my question. Thanks.
thank you.
Great. Was there anyone else that had any questions? No, that seems to be it. And that draws. Do you have any final thoughts, Farid? Anything you want to add?
I just want to say thank you for organizing this event, mate. Absolutely talented person as you are. Natural leader. You led this webinar as well. And it's nothing short of a perfect webinar that we have this year with your help. Much appreciated.
Thank you. I appreciate that. And so on that note, that draws to a close the 7th International Webinar on Construction Materials. On behalf of the Institute of Construction Materials, I would like to extend a thanks to our speakers, Akmal and Wafaey. We really appreciate your participation and your really insightful and informative presentations. The knowledge shared here has been invaluable, and I'm confident it will inspire continued progress and collaboration in the construction industry. So once again, thank you for your participation, and to all of our attendees, thank you for joining us this morning. We appreciate your attendance and enjoy the rest of your weekend.
Thank you all.
Thanks,
Have a good
everyone.
one. Cheers.
Bye.